We want to be able to make predictions about how anions affect water and their acidity levels. Well, anions by default are basic unless they come from strong acids, so the chloride, the bromide, the iodide ion. Those don't affect pH, but fluoride, for example, will affect the pH. And in general, what happens is anions will extract a proton from water through a hydrolysis reaction to leave behind hydroxide. And the degree of hydroxide that's left behind is based off of the Kb value. Likewise, reactions involving cations produce a acidic solution. So I probably shouldn't have said will lower the pH. It just means making the solution more acidic. So if the cation doesn't come from a strong base, then it will make the solution more acidic because it will extract an OH molecule from water, leaving behind an H plus or a hydronium ion, as the cartoon shows. So cations make things acidic, anions make things more basic, and so when we look at competing factors that control the pH of a solution, we have to look at which one is bigger. That is, which one has a greater magnitude, Ka or Kb. So if you have two ions, both of them that are weak, then you have to look at the Ka and Kb value, and whichever ion has the larger magnitude constant will control the pH of a solution. Now, some trends that we see with cations is that as the size of the ion gets smaller, it becomes a better acid. Likewise, increasing the charge on the ion increases the acidity level. So things that have a +2 charge aren't as acidic as things with a +3 charge. And again, we don't normally think about ions as being acidic or basic, aside from H plus and OH minus, but it turns out they are. So what are the net effects of cations and anions in solution? Well, an anion that is the conjugate base of a strong acid does not affect the pH of solution. An anion that is a conjugate base of a weak acid will increase the pH, making it more acidic, more basic, makes it more alkaline. A cation that is the conjugate acid of a weak base will make the solution more acidic. Cations of the strong Arrhenius bases do not affect pH. All other metal ions will cause a decrease in pH, resulting in a more acidic solution. And again, when you have to compare two ions, one a cation and an anion, you have to look for which value is bigger, the Ka of the ion or the Kb of the ion. Switching gears and talking about binary acid strengths, we can make some predictions. And what we find is that more polar bonds lead to greater acidic conditions. And as we move from left to right on the periodic table, we become more acidic, and that again goes back to polarity of the hydrogen bond with the rest of the molecule. And we also find that size causes acidity to increase. So as we move down the periodic table, we increase acidic strength. And that's because the hydrogen ion is really small compared to the anions that are being paired up with. And so hydrogen likes to have lots of surface contact with other things or bond to things with relatively the same size. And as you move down the periodic table, those principal quantum numbers increase, meaning the size of the atom or ion gets bigger and bigger, which means there's less interaction between the hydrogen ion and what it's attached to, resulting in a weaker bond. So we see HF is a weak acid, for example, because hydrogen and fluoride are about the same size. It's a very polar bond. But when we move from HF to HCl, chloride's a much bigger ion, and as a result of that, hydrogen can't hang on nearly as well, and so it becomes an ionic bond at that point, whereas HF was a covalent bond. And as we go from covalent to ionic, it means that the separation is a lot easier to occur, and so the acid strength increases. We would predict hydrobromic acid is even a stronger acid than hydrochloric because the size continues to increase as we move down the periodic table. So those are some factors that affect binary acid strength. Oxyacids are acids which we have some sort of halogen with a OH group attached to it. And what we find with that is as we attach more electronegative elements, the more acidic it becomes. So H2O, the very bottom one on that list there, it's got some electronegativity, but the dissociation constant's relatively small. We go to hypoiodous acid. Well, the electronegativity is a little bit greater than that of water, so it becomes a slightly better acid. Hypobromous acid, bromine's more electronegative than iodine, so again we see an increase in electronegativity and acid dissociation constant. And chloride, even more so. And so as we work our way up from iodide, bromine, and chlorine, those halogens on the table, we become more acidic. But we can also increase the acid strength of an oxyacid by increasing the number of oxygens that it has. So one oxygen makes it acidic, then two would increase the acidity level, whether it's attached to a bromide, an iodide, or a chloride. And so you can see here, by the time we attach 4 oxygens to a chloride ion and we form perchloric acid, we're a strong acid compared to hypochlorous acid, which was a fairly weak acid. Now, something else that can affect oxyacid strength is resonance. If you have the opportunity to have resonance, which recall means you have a double bond that can be placed in more than one position but still keep the structure of the overall molecule, that essentially means you have a resonance structure where the double bond actually gets stretched over both areas that the bond could be. And so that helps stabilize the molecule. So resonance structures actually help increase the acidity of an oxyion. Now the last type of acid and base we have to talk about is what's known as Lewis acids. Lewis acid, the last type of acid-base theory we need to talk about is Lewis acid-base theory. Lewis acids are defined as electron pair acceptors. These are molecules which don't have a complete octet around them and are perfectly fine at taking a lone pair of electrons from another molecule. So, for example, boron trifluoride is a Lewis acid. It has an empty valence orbital which can be filled by electrons from another molecule. Lewis bases are electron pair donors. So NH3, or ammonia, is a Lewis base. And what we find is that under Lewis acid-base theory, molecules that are acids under Arrhenius or Bronsted-Lowry are still acids, and bases, which are bases under Bronsted-Lowry and Arrhenius, are still Lewis bases. So anything that can donate a lone pair of electrons we describe as being a Lewis base.